Good day, good people. Let us look at the application of the gradually applied. Let us look at the gradually applied load. No? I will be applying that which we spoke about, the gradually applied, looking at exercise 2, number 4 in our blue books. Okay, I'm looking at this right now. We are given a member consists of 3 sections. Yeah? That which it is given, it consists of 3 sections. The first part is a pipe with an outside diameter of 80 mil, and its length is 600 mil. The second section is a solid bar with a length of 200 and a diameter of 100. The third section is 50 mil square bar with a length of, now let us project that which it is given. Right, we are given this. Okay, we are given the outside diameter, the D out. Then they want us, we don't have the D in. Then we are having the solid substance as well. We are given the solid substance. Right, the solid substance as well, it's a round bar. It is solid. Then the third one, it's a square. Right, 50 by 50. Then we are given various length. The L, the length for this one, it is 500. Then for this one, the second one, the length, it is 200. Then this one, the length, it is 600. All right, they are all in mil. Then the diameter of this one, it is given as 100. Then this one, we are only given the 80, D out, it is 80 mil. Then the first question, they want us to calculate the inside diameter. And we are given the strain as well. Then we are given the strain. We are given the Young modulus, it is 210 gigapascal. Then we are given the force tensile, it is 200 kilonewton. Then we are given the strain, it is 7,548, 10 times to the power negative 4. Strain doesn't have the SI unit. Now, before we continue, let me bring your mind a bit in your strain energy, the formulas that we are using when we are given compounded material. In calculating the strain, the total strain energy, it will be U1 plus U2. Isn't it, plus U3, whereby U, when we calculate U, it is F squared L over 2AE. This is under, this strain, it is under the gradually applied load. Then we have the formula of calculating the total change in length. We know that it is FL over AE, whereby if it's a compounded like this, it will be plus FL over E plus FL over AE, whereby it is X1 plus X2 plus X3. Then we get the total change. Now, let's look therefore, if we are given the Young modulus and they want us to calculate the strain, we know that we first have to calculate the stress, and the stress, it is always, the stress max, it is calculated from the smallest area. Please make note. The stress, it is calculated from the smallest area. It will be force over area. If they want you to calculate the force applied, you must always calculate the force. This force, it must be always calculated from what? Maximum stress and the smallest what? Area. Between the 3, we then have to look at the smallest area. By the look of things, but we'll see when we calculate. Right, please make note that the maximum stress, it is always calculated from what? From the smallest area. Then if we are given Young modulus and they want us to calculate strain, it will be stress over strain. Then we can make strain, the subject of the formula, then it will be strain equals to stress over Young modulus. Now, in calculating the strain when given the compounded material like this, it will be strain total equals to strain 1 plus strain 2 plus strain 3. Now, the strain obviously is taken from what? From the change. Whenever there's a change in length, you must know that that material is bound to experience what? The strain. Now, this is the formula. That another formula for strain, it will be the change in length over length original. Yeah? You can use that formula as well. But the yes. And we know as well the formula of calculating stress, it is force over area. At times when coming to strength, it's a question of playing with what? With formulas, okay? Now, going back a bit to the given information, let's read. They said a tension of 200 kilonewton is applied to the member and causes a total strain. Now, it means this, it's what? It's a total strain. This is a total strain. Right, and the first question they want us to calculate the inside diameter of the pipe. Now, they want us to calculate this diameter here. They want us to calculate this diameter here, the inside diameter. Right. Now, let us go ahead and calculate that. Right. Now, in calculating the inside diameter, we will use this formula. The fact that we are given the strain total, we will say strain 1 plus strain 2 plus strain 3. Right. We know that the formula of calculating strain, let's write it. We know the formulas of calculating strain. There are they. I've indicated to you. I'm having this formula, that formula, in calculating what? The strain. Now, we will be using one of them. We will use what? One of them. We will use this one in calculating the strain. We will use this formula here. Right. Now, we know that in calculating the strain, based on the given information, we are having stress over Young modulus. What is the formula for stress? It is force over area. Now, let's go ahead and substitute here the strains with the given formulas. It is stress over Young modulus 1 plus stress 2 over Young modulus 1 plus stress 3 divided by Young modulus 1. Now, why I'm writing 1? Because on the given information, they said the second bar is the third bar, all the sections. Now, I'm using that as because I'm checking the given statements here. All the sections are the same material, and E equals 2. Yeah? That is why I'm saying E1, because it is what? It is common. Okay? Now, this is what we have here. Now, let's take out the common factor. It is 1 over E, stress 1 plus stress 2 plus stress 3. Now, how do we calculate stress? This is the formula of calculating stress. Now, I'm having 1 over E equals to force over area 1 plus force over area 2 plus force over area 3. Force, it is common as well, because the force applied here, we are told that it is the tensile force. Now, as a result of the tensile force, it will cause the strain here, it will cause the strain on unit 2 and unit 3. Right, this is what we have. Can we then take out the common factor here? We can then take out the common factor, of which the common factor, it is the F there. Then I'm having force over E, open bracket, 1 over area 1, plus 1 over area 2, plus 1 over area 3. The fact that we've taken out what? The common factor. Now, let us then calculate the area of the second section, because it's a solid one. We are given the diameter and the length, and we can calculate as well the area of what? Of the third section. We are given the square there. They said it is 50 by 50. There it is. And the third section is a 50 mil square bar with the length of 500. Now, let's go ahead and calculate the areas there. Let's use a different ink there. For area 1, it is pi d squared divided by 4. We are having pi multiplied by 0.1 squared divided by 4. Then we get our answer as 0.0078 meter squared. Then the area 3, it will be, this is for area 2. The area 1 we don't have. Then the area 3, it is square. Then it will be 0.05 multiplied by 0.05. It is length times length. It's a square. Then we get our answer 0.0025 meter squared. Right. We've now managed to calculate the areas. Then we can then go ahead and substitute from this formula there. Do we have force? Yes, we do have force. Force, it is 200, 10 times to the power 3, divide by Young modulus, it is given as 210, 10 times to the power 9, open bracket, 1 over area 1, we are looking for the inner diameter, plus 1 over area 2, we did calculate it, 0.00778, plus 1 over 0.0025, close bracket. Then remember, equals to total strain. Don't forget about the value of your total strain. Let's write it somewhere here. The value of total strain, it is given as 7,548, 10 times to the power negative 4. Right. Don't forget it. But we are coming on that one. Now, then here we are having, it will be the 10 to the power 3, it will be cancelled from there. Then you are having 200 over 210, 10 times to the power 6. Then it will be 1 over A plus 127,389 plus 400. Plus 400. Right. When you add the two, then this is what you will have here. You will have 0.952, 10 times to the power negative 6, open bracket, 1 over A plus 527,389. Right. Let's jump to the other page. Then we are having strain. Remember the strain there, it is 7,548, 10 times to the power negative 4 equals to 0.952, 10 times to the power negative 6, open bracket, 1 over A plus, we said it is 527,389. Right. Then we'll then divide the left hand side and the right hand side by 0.95. Then we are having 7,548, 10 times to the power negative 4, divide by 0.952, 10 times to the power negative 6, equals to 1 over A plus 527,389. Right. Then this side will lend ourselves, when we are punching in a calculator, with 792,54. Right. Then we'll summary transpose that one to the other side, minus 527,389 equals to 1 over A. Then I have my answer here as 265,151. Right, equals to 1 over A. Then when I cross multiply in making A the subject of the formula, I will have 256,151. A equals to 1. Then A would be 1 over 25, not 5, it will be 256,151. Then I get my answer, the area there, I get my area as 0,00377 meter square. Now this is my area, but they said we should calculate the inner diameter. Now in calculating the inner diameter, I'm having d squared minus small d squared divided by 4 all squared equals to 0,00377. Eh? Right, then let's write the portion there. Right, then I'm having negative d squared equals to 0,00377 multiplied by 4 divide by pi minus the big D. We are given the big D as what? We are given the big D as 80. Okay, we are given the big D as 80. Then it will be minus 0,08 squared. Then we get our answer there as I get my answer there as negative. Please verify it for me. 0,00159. Yeah? Then the negative and the negative will cancel out. Then D would be 0,00159. Then I get my diameter as 39,976 millimeters, and of which when we round it off it will be 40 millimeters. Now this is how you calculate the first question, calculating the inner diameter. Yeah, in calculating the inner diameter. Now let's look at the second question there. On the second question, they want us to calculate, let's increase my workspace. Bear with me, I'm increasing my workspace. Let's cancel this one. Right, okay. Small font. Right, then in calculating, the second question and the third question would be easy. They want us to calculate the total change in length, okay? They want us to calculate the total change in length, and in calculating the total change in length, that means we will be using x1 plus x2 plus x3, right? They want us to calculate the total change in length. Now, in calculating the total change in length, we know that. Now, let me say to you, if this is the formula to use in calculating the total change in length. Né? Like I said, good people, at times it's a question of playing with with formulas. We know that here we are having a stress. It will be stress 1 over E. I mean to say E, not A. Right, it will be E plus stress 2, L1, L2 over E. E, it is common, plus stress 3, L3 over E. E, it is common. You can use this formula, or you can use this one, or you can use this one. Right, or in solving it, you can use this one from this formula here. Okay, you can take out the common factor, and of which the common factor on this formula, it is F, and another common factor at the bottom, it is what? It is E. Then I'm having L over A plus 1 plus L2 over A2 plus L3 over A3. Right. Now, we've already calculated this one. 200 times 10 to the power 3 over 210, 10 times to the power 9. It's a giga. We've already worked with it, isn't it? Then here we are having 0.6 over the area. Remember the area, we have it. There it is, the area of the first unit. There it is. Now it's a question of us substituting there, because we did calculate the area. Right, it is 0, 0.00377 plus the length of the second, it is 0.2. The area 0.00785 plus the third one, it is 0.0025. Right, now if you can look at these areas, you can tell that the smallest area it is this one, because you are having 0.003, 0.007, 0.002. That means the smallest area it is this one. The maximum stress we have to calculate it from this one here. Right, then this side we've already calculated this one. It is 0.95, it is 952, 10 times to the power negative 6, open bracket, 159, 15 plus 25 plus 478, because when you 0.6 divide by the area, 0.2 divide by the area, you'll get this number. It's a comma here, not plus, it's a comma here. Okay, let's wipe here. It's a comma here. It is 25, 478 plus 0.5, okay. Okay, 0.5 divided by 0.025, then you will get your answer there as what as 200. Then when you add this inside and multiplying by 0.952, then you get your change in length as 0.00366 meters. Then in rounding it off to millimeters, it will be 0.366 millimeters. Okay, this is how you apply it. Then the third question from that one, they want us to calculate the maximum stress in the members, the maximum stress in the member. Now, like I said, that the maximum stress, we will calculate it from the smallest area, and the smallest area, it is that one of 50 by 50, the square one. Then I'm having a force of 200 divided by 0.0025, then I get my stress, maximum stress as 80 megapascal. Now, this is how you tackle the third equation. Then in calculating the last question, let's wipe here. In calculating the last question, they want us to calculate the total strain. Now check this. It is the formula of calculating the strain as well. Now the only difference is that we need to put the square there and multiply by what? By 2 there. Remember the formula of calculating the strain, it is F squared L over 2AE. Right, now here we are having exactly this here. We took out the common factor, it is F squared, then we took out the common factor, it is 2E. Then hence here we wrote that number. Now I will tackle that one. I'm not going to start it from scratch because we've already worked it out. There it is there. It will be 200, that 200 there, like I'm doing here. We will take this one in calculating the total strain, this one here. But now the only thing that I'm doing here, it is to put, let's use the red pen. You will put the 200 under square because the formula, it is F squared. Then here we will multiply by what? Multiply by 2 because the formula wants us to multiply by 2. Then from this formula here, from that formula here, then we have, from this formula there, we have UT equals to, from that formula, we are having UT. Please punch these things, but don't forget to put the F under square and this one to multiply it by 2. Then you will have, the answer would be UT equals to 0.0952 multiplied by 384,629. Then we get our strain energy as 36,6 joules. Right. Please don't forget that from here you go somewhere there, because this, remember what is the definition of strain? Don't forget the definition of strain. They said, what's that definition of strain? Nonetheless, strain is defined as the energy stored in the body due to transformation. Right. Now, due to transformation, hence I calculated the strain energy from this transformation. This is the formula of transformation. The only thing that you do, you put a square there. The only thing that you do here, you put a square, you multiply by 2, you put a square, multiply by 2, put a square, multiply by 2. Common factor, it will be f squared 2e, f squared 2e. There it is, f squared 2e. Then we got what? The strain energy. This is how you apply. This is one of the questions in application of what? Of gradually applied load. Thank you, good people.